Principia for short, and it is Latin for the mathematical principles of natural philosophy.
The mass and energy were in fact equivalent, according to the formula mentioned above.
In 1894, a high school teacher unknowingly set in motion a chain of events that would shape the course of history. Advising a discontented student to leave, that teenager faced rejection from prestigious universities and settled for a humble clerk job at a patent office. Little did the world know that this seemingly ordinary young man would go on to revolutionize physics and redefine our understanding of reality. His name, Albert Einstein. Stay tuned as we explore the thought experiment that sparked Einstein's journey, leading to the most significant revolution in physics since Isaac Newton. The story unfolds, revealing the origins of Einstein's groundbreaking theory of general relativity and its far-reaching impact on our perception of the universe. This is Reveal the Mystery. If you are curious to learn mysteries of the world, space, and beyond, consider subscribing. Isaac Newton. Discussing Einstein necessitates a mention of the classical physicist Sir Isaac Newton. In 1687, Newton released his work Mathematical Principles of Natural Philosophy, wherein he elucidated his 3 laws of motion and the law of gravity. This publication stands as a pivotal text in human history. Prompted by observing a falling apple, Newton posed a crucial question: if the apple falls, does the moon also fall? These inquiries propelled him to unveil the law of gravity, asserting that every object in the universe exerts a force of attraction on another. This force is accountable for Earth's gravitational pull, orbit around Earth, and, fundamentally, the existence of the universe. However, Newton's queries persisted, such as the reasons behind objects attracting each other, the source of gravity, and the peculiarities of Mercury's orbital movement. Albert Einstein. The mystery endured until the time of Albert Einstein. In 1915, Einstein introduced his theory of general relativity, a conceptual umbrella that essentially encompasses his gravitational theory. Within this theoretical framework, Einstein clarified the essence and source of gravity, tackling questions that had previously confounded Newton, such as the intricacies of Mercury's precession. Taking a step back to 1905, a pivotal year in Einstein's intellectual journey, he introduced his theory of special relativity. This theory delved into the speed of light and the motion of objects, effectively describing non-accelerating entities. However, it faltered in the presence of gravity or acceleration, leaving some unresolved aspects. A breakthrough occurred in 1907 when Einstein, inspired by observing a window washer on a ladder, had an epiphany. Contemplating what he would experience while falling, he realized that in free fall, gravity wouldn't exert pressure, leading to a state of weightlessness. This insight connected some puzzle pieces, yet Einstein's quest for a comprehensive understanding persisted. Further reflections on falling, this time in a windowless room, brought about another revelation. Einstein envisioned being in a spacecraft moving upward with the same gravitational acceleration as on Earth. In this scenario, an observer inside the spacecraft would be unable to distinguish whether they were in motion or stationary on Earth, an insight known as the equivalence principle. The equivalence principle posits that an object accelerating freely in the absence of gravitational influence is essentially indistinguishable from an object at rest on Earth, subject to gravity. This realization became pivotal in unifying Einstein's special theory of relativity with gravity. Notably, Einstein did not halt his exploration at this point, continuing to refine and expand his theories. He conducted another thought experiment, this time envisioning the outcome of directing a laser beam from one side of a room to the other. In the scenario of the room being within a spaceship ascending with the same acceleration as Earth, he theorized that the beam's height would slightly decrease on the opposite side due to the upward movement of the floor curving the light downward. This bending of light, however, would only occur in a space setting. On Earth, the light would appear straight. It's worth taking a moment to marvel at his intellectual prowess for orchestrating such mental experiments. Despite these intriguing insights, Einstein remained skeptical as they appeared to contradict the principle of equivalence. The acceleration within the spaceship and under the influence of gravity should yield identical results in terms of height. He concluded that the only plausible explanation was the bending of the light beam under the influence of gravity. The next challenge was to understand the meaning of this light bending. Einstein, railing on his profound imagination, proposed that light follows the shortest and straightest path it can, suggesting that in space, where there is no visually objective straight path, inherent curvature exists. This groundbreaking idea reshaped scientific history by suggesting that space curves in the presence of gravity, creating the illusion of a curved light beam. Einstein hypothesized that the presence of matter or energy in space induces curvature, leading to the realization that matter and energy warp space-time, causing nearby objects to fall towards them. To illustrate this concept, there is a popular analogy often depicted in videos. Envision a trampoline with two types of masses, a heavy metal chunk and a piece of marble. Placing the metal on the trampoline causes it to bend, and as the marble is rolled on the surface, it orbits the heavy metal. This analogy demonstrates that no force is directly acting on the marble, yet it orbits around the heavy metal. Extending this analogy, Einstein proposed that the same principle applies to celestial bodies, with the Sun acting as the heavy metal and creating a curvature in space that influences the orbit of Earth and other objects in the universe. According to Einstein, the presence of matter and energy warps space-time, compelling nearby objects to move towards them. Another significant facet of his theory involves the incorporation of not only the three spatial dimensions but also time, leading to the concept of space-time. The inclusion of time stems from his earlier theory, which asserts that the speed of light remains constant for observers in any frame of reference, regardless of whether an object is in motion or at rest. To exemplify this, consider a scenario where a light beam travels from point A to point B. If a massive object, like our Sun, is situated between these points, it will curve the light's path, elongating the distance between point A and point B. Consequently, the time taken for the light to traverse this distance increases in the presence of the Sun. This concept initially appears to contradict the theory of special relativity, which asserts the independence of the speed of light from the frame of reference. According to this theory, whether the light beam travels freely or under the influence of a gravitational field, it should take the same amount of time to move from A to B. To reconcile this apparent discrepancy, time itself must undergo alterations. In other words, time decelerates in proximity to a massive object in space and accelerates when one is farther away. This phenomenon, termed gravitational time dilation, has been substantiated through various empirical experiments. As a concrete example, time for individuals on Earth progresses more slowly than for astronauts aboard the ISS, providing a tangible demonstration of how gravitational forces affect the passage of time. Gravitational lensing. A century ago, Einstein's ideas were largely dismissed, but just 4 years after the publication of his general theory of relativity, astronomer Sir Arthur Eddington conducted an experiment to validate it. According to general relativity, the Sun should induce a warp in space, causing light beams to bend and altering the position of stars behind the Sun. Eddington's experiment supported Einstein's theory, establishing the phenomenon now known as gravitational lensing. This groundbreaking experiment marked the initial validation of Einstein's theory, capturing global attention. Today, ample evidence supports Einstein's theory, with predictions made a century ago being confirmed in contemporary observations. These confirmations have opened a new observational window into the universe.